In this video, we're going to take a look at the different structures of our various coenzymes. And what we'll see is that they're going to use some of the building blocks that are used from each of the four major classes of biomolecules. So we'll be using some of those amino acid building blocks from our proteins, some of the nucleotides from our nucleic acids. We'll be using glucose in an example, as well as some lipid building blocks. So looking at some of the structures, recall our amino acids have that alpha carbon on it that's substituted with an amino group, a carboxylic acid, a hydrogen atom, and then some side chain R group that's highlighted in the peach structures there. Today in this topic, we'll be looking at the amino acid serine, methionine, lysine, and glutamate. Within our nucleic acid components, we'll be looking at two of these, the structures of uracil and adenine, and these will be bound to one of the ribose 5-carbon sugars. So we'll look at that in just a moment. With respect to the carbohydrates, we'll be looking at glucose, which is one of the predominant carbohydrates in our body. So just recognizing it with the 6 atoms in the ring that does contain an oxygen, and then we have numerous hydroxyl groups coming off of that ring as substituents. With respect to our lipids, some of the examples we'll look at will contain that isoprene 5-carbon unit that's located at the top of the slide. Looking more closely at our amino acids, as I said, we'll be largely looking at things that contain adenosine in them. And for these structures, we'll be looking at the adenosine. It will be bound to the ribose 5-membered ring, and we'll be looking at various substitutions with respect to the phosphate groups coming off of it. We'll also look at an example that has the uridylate or uridine structure in it, whereas the adenosine is going to be one of our purine bases with those 2 fused rings and the amine coming off the top. Our uridine is going to be one of the pyrimidine bases. And we'll look at different substitutions on specifically the adenosine. So adenosine, we'll first look at adenosine triphosphate or ATP. As the name implies, it's got 3 phosphate groups that are coming off of that ribose sugar. Our adenosine diphosphate just has 2 of the phosphate groups bound to the ribose sugar. The structure of inorganic phosphate is shown to the left of that. And our adenosine monophosphate just has a single phosphate bound to it, and your structure of inorganic pyrophosphate is shown there to the left. This can also be hydrolyzed to give you 2 molecules of inorganic phosphate. Other structures we're going to look at that you should be familiar with are the nicotinic acid, which is just simply a pyridine that has a single carboxylic acid substituent at the 3 position. That's the structure in our vitamin niacin. We can convert that carboxylic acid into an amide to form this nicotinamide, and we'll look at its incorporation into coenzymes. Our PABA is para-amino benzylic acid. So we're going to have a benzene ring. We have a carboxylic acid on that. And then we have a para, so at the 4 position, amino group. So these are the building blocks we'll be looking at to use to build up some of our coenzyme structures. We're going to start with our metabolite coenzymes. So we've only talked about 3 of the metabolite coenzymes. They're all shown here. They all contain a nucleotide. We'll start with our ATP. right? So ATP, the structure is shown there. We're highlighting the AMP moiety in blue that's with a single phosphate group. If we have a second phosphate, that's our ADP. And then if we add the third pink phosphate, that's the structure of ATP. So this can serve as a phosphoryl group donor. We also said it can donate possibly even the adenylyl groups. But right now we're just trying to get the structures. If we look at the structure right below it, this is going to contain the uridine diphosphate. So similar to the ADP structure, we have one of our nucleotide bases. In this instance, it's a uridine rather than adenosine. And we have our sugar. We're going to have 2 phosphate groups. And then in pink is our glucose. So UDP glucose is used in some different transfer reactions. And it's just built using some of our nucleotide building blocks and one of our carbohydrates. Our last metabolite coenzyme is S-adenosylmethionine, or SAM. SAM, just as the name implies, is going to contain an adenosine. So this time we have our purine base at the top bound to our sugar. But then rather than being bound to some phosphate groups, we're going to form a covalent bond between the CH2 group and our sulfur atom on methionine. So that does make our methionine the other one of our amino acid building blocks as the other part or other half of that coenzyme. And we're just highlighting in pink there that methyl group. SAM, of course, is one of our methyl donors. So you want to be able to pick that out. Next up, we're going to try to continue, rather than go in the vitamin order, we're going to stick with vitamins or coenzymes that have similar groups present. And here we're going to stick with those having some type of adenosine monophosphate or adenosine diphosphate present in it. So first up, we're going to look at our flavoenzymes. We have 2, we'll just talk about we'll just talk about the oxidized form. So we have 2 oxidized forms, our flavin mononucleotide, FMN. And so what we're going to have is the isoalizoxazine ring system, highlighted in green, that's present in all the flavins. So panel A is our riboflavin vitamin. You see we do have another sugar, ribitol, coming down. It's linear rather than being cyclical. So our first flavo-containing nucleotide, all we're going to do is add a phosphate group onto our sugar. So if we were to end this structure just with the black, that would be our FMN, flavin mononucleotide, so single nucleotide. If instead of stopping with one phosphate, we also added the AMP, shown in blue, onto that phosphorus, this gives us our structure of FAD, or flavin adenine, right? So it's even in the name that it has the adenine dinucleotide. So that will be our structure of FAD, is the complete B structure. Sticking with things that contain AMP or ADP, we can move on to our B3, our niacin containing coenzymes. In this, we have, again, 2 of these, an NAD as well as NADP. The only difference in our 2 structures is the presence of that additional phosphate group coming off of our sugar with NADP. So if we break down this structure, essentially what we're going to have is AMP at the bottom. It's already bracketed for you. So we, again, are having that AMP present. And then what we've done is we've taken our nicotinamide, shown there. We've attached it onto another sugar molecule that has a phosphate. So that gives us our nicotinamide mononucleotide. When we add to that the AMP, we get our nicotinamide adenine dinucleotide, and then with the phosphate we get the NADP+. The key thing with our nicotinamide, for our reactions to happen here, we don't want any substituents on that nicotinic acid or nicotinamide ring. All the action with our hydride transfer is going to take place at that 4 position, which is why it's highlighted. So in the reduced form, we'll be transferring a hydride from our coenzyme to the substrate. With the oxidation, we are going to be transferring a hydride from our main substrate onto our nicotinamide coenzyme. It'll be accepting that hydride at that 4 position as well. A similar related molecule to the nicotinamide ring is going to be our pyridoxine or pyridoxyl vitamin, which forms the pyridoxal 5-phosphate coenzyme. You notice on this ring we still have, and we'll just use the pyridoxal for an example, it is also, just like the nicotinamide, a pyridine ring system that's substituted. Unlike the NAD and NADP, we have multiple substituents. For now, we're not going to be concerned with those. What we're focused on is having that pyridine ring with that aldehyde functionality at the 4 position. So it's highlighted here in the actual coenzyme form. Additionally, we're going to attach a phosphate onto the 5 position. The aldehyde's functionality is really critical because this is our coenzyme that's going to be forming a Schiff base with a lysine side chain on our enzyme, so it needs to be able to form that Schiff base, so we need that aldehyde. Okay, looking at our B12, we've put it on here because you do have the potential for another adenosine incorporation into this, adenosylcobalamin vitamin B12. That's highlighted there. The biggest distinguishing feature, though, of vitamin B12 is the cobalt. So you can see it over here on the left on the top panel or in the right structure. The presence of that cobalt is necessary for this coenzyme to carry out its functions. Sticking with other coenzymes that are going to contain some type of ADP-like unit, we'll look at our coenzyme A. And this figure nicely has our components broken down. We once again see ADP, so you should be able to now recognize that structure. Again, it's one of our purine bases. We then have a pantothenate unit followed by mercaptoethylene, where this is the thiol is our reactive group that's critical for our chemistry to take place. What we can do, and this is coenzyme A, what we can do with coenzyme A is actually replace our ADP molecule with a serine side chain on our protein, so that's shown here in blue. And what that gives us is acyl carrier protein. So it still has that thiol that's reactive, so this will be involved in some acyl group transfer reactions, just as our coenzyme A. We now have our tetrahydrofolate, so this one does not have an adenosine. We still have a ring system. This time it's the pterin ring system rather than a purine base. But we'll look at the other partners, which you should be able to identify. And if we look at structure B, in blue we have a glutamate side chain. That's one of our amino acid building blocks. Next to that, we have in pink our PABA, and we just mentioned PABA, para-aminobenzoic acid. And then we got that tyrrin ring system in black. Now that glutamate, so that's our B, has our folate in the body for the coenzyme to be active. It is going to end up polymerizing with additional glutamate units. So we'll be forming some additional peptide bonds here, and we'll typically have between 5 to 6 glutamates in that linear polymer there coming off of the glutamate. So you should be able to recognize those pieces. Our folate is the only coenzyme that has a glutamate incorporated into it, as well as the PABA. Some of these structures we'll encounter again when we get into the Foundations 3 with some of our antibiotics. Now, a couple where I don't necessarily expect you to memorize the entire structure. These are kind of the misfits that don't necessarily contain those building blocks that we've been using from our 4 major classes of biopolymers. We do have a pyrimidine ring, which you may be familiar with, that nitrogen containing ring. We are also, it has a thiazolium ring there highlighted in green. It's similar to your 5-membered imidazole ring that we see with histidine. We now have a sulfur present in that 5-membered ring though. This is another coenzyme that gets phosphorylated. This is the only one where we're attaching 2 phosphates or a diphosphate onto it. So that's really what I'd look for if I were to ask you about this structure, is that diphosphate moiety. Lastly, we're coming up on our ubiquinone. So ubiquinone, just as the name says, it's going to have a quinone. So the quinone functionality is shown in the pink. It's just simply a 6-membered ring that can, in the reduced form, it's a benzene ring with 2 para-hydroxyl groups. In the oxidized form, or actual quinone form, we have 2 carbonyl groups para to one another. So that's somewhat different. Additionally, from our lipid group, this is the first one we're actually using one of our lipid building blocks. We're going to incorporate these isoprene units. So an isoprene is this 5-carbon building block shown on the slide, where we do have a couple carbon-carbon double bonds present. So the ubiquinone structure is going to incorporate multiple isoprene units coming off as a substituent on the ring system. We have 6 to 10 of these usually. This is also known as our coenzyme Q. So some people take like a CoQ10. That this will be what they're referring to, where they got 10 of those isoprene units coming off of it. These last structures, so our biotin coenzyme will be bound to the enzyme through a lysine, and this is just a amide bond linkage. With the biotin, I'm more likely to ask you to recognize the reaction it catalyzes, since it's unusual, where we're using this bicarbonate as well as ATP to carry out a carboxylation reaction. So here we're going to carboxylate our enol pyruvate in order to form oxaloacetate. In our last coenzyme, similarly to the biotin, it is bound through an amide bond to our lysine side chain. This is lipoamide. It does contain this unusual 5-membered ring containing a sulfur-sulfur double bond, which is important for the chemistry. So that would be really your distinguishing feature for this coenzyme. All right, so that wraps up that topic.